One sec.
You guys see me now? Yeah. Yeah, good catch there. That was, I don't think we were recording actually.
I see the icon now on my screen.
Okay, great. Yes. Yeah, I see it too. So, yeah, good catch. Thanks. All right. We can then proceed. I think everyone is back in now. And actually, I'm going to take this opportunity to take a picture of all of you for the roll call. All right. So I'm going to share the screen now. And all right, so you guys can, I'm assuming you're seeing the PowerPoint. All right, so I was saying that, so we're recording now, that's good. I was saying that information assurance is the practice of managing risks while maintaining the properties that we just discussed. So the properties of, confidentiality, integrity, availability, non-repudiation, and authentication. Malicious human threats are not the only kind of information, that information assurance considers. Hungry squirrel might, destroy a cable, right? So that's also something to worry about. So this is about protecting the information system, but not necessarily about cybersecurity. Whereas the Siena principles are really about the properties of data in the states of being stored, being transmitted, processed, etc. So here, this is where we, although it seems trivial, I know it seems trivial to define confidentiality and integrity because, I get this every semester from students. They're like, yeah, I know what that is. Okay, someone else. All right. So although it seems trivial, confidentiality, integrity, you're going to see as we start thinking about cryptography and what we're achieving, that it gets a little bit more complex because you really have to understand how cryptography works. But I think you'll enjoy once we get to the point of it, the subtle difference or the differences. So let's think about first provide some definitions of all of these. So confidentiality is assurance that information is not disclosed to unauthorized individuals, processes, or devices. And so we want to protect the information. Integrity means no unauthorized modification or destruction of information. Like I said on Tuesday, you can have a file that is 1 billion bytes in size or whatever, but if you just change one bit of it, you have affected the integrity of it. And so we want to have ways of dealing with that. So the quality of an information system reflecting the logical correctness and reliability of the operating system, the logical completeness of the hardware and software, and the consistency of the data structures and the stored data, right? So that's really what integrity is. Availability, this is the one that is indirectly related to cryptography. It basically just means timely, reliable access to data and information services for authorized users. So this is when you want your systems not to go down. Okay, you want the system not to go down. Now, non-repudiation is an interesting one, and we will look at examples of this, but it's the assurance that the sender of data is provided with proof of delivery, and that the recipient is provided with proof of the sender's identity. So neither can later deny having processed the data. And that's really the key. That non-repudiation is that, oh, you can't say, no, I did this, but then you say, no, I didn't do it. You know, you can't say that, right? So you own up to what you said or what you did. And that's what non-repudiation is. And so it has to do with identity. And we're going to see how, you know, that can be done very interestingly in cryptography, with cryptography. Then we have authentication, okay? And authentication is a security measure designed to establish the validity of a transmission message or originator, or a means of verifying an individual's authorization to receive specific categories of information. So authentication just has to do with, you know, I am who I say I am, right? So I authenticate into the system. The most familiar example of this is passwords. We also know biometrics, but actually here we're going to be using cryptography. Every day that you connect with your browser to things like your bank, Brightspace, Netflix, Amazon, places like that, you're using a type of cryptographic authentication. And so we're gonna take a look at that and how we can make that happen. But before introducing that topic, really what we're gonna do is we're gonna ask some fundamental questions about it. Okay? So understanding that stuff, right, in terms of the 5 pillars, that's really the goal, right? Whenever you think of security, you want to think in terms of the 5 pillars. Understanding something as an attack requires understanding which of the 5 pillars has been violated. You know, or another way of saying it is which property is lost. So the best way to understand this is to look at some examples. So let's review a few of the bad things that can happen and understand them with examples. So here's an example. All right. You injected HTML code, right? So you guys have taken 110, you know about JavaScript and HTML, right? Web. And so web has security issues, right? Websites, we know that, you know, websites can get hacked. But here, all we want to do is think about which of the pillars has been affected. So let's think about it. So I have a script there, right? There's a script, or maybe it looks like the one at the bottom, right? And there's a message board. So the message board has text boxes, right? So it's got text areas, text boxes, it's got buttons. And then somebody puts that JavaScript in there. And then here it says which pillar is violated. And so the answer is this attack essentially makes the message board impossible to read. So this is an attack on availability, right? So now keep in mind on the exam, I like to ask these types of questions. So I like to give you like a little problem like this, and then I'll say, okay, which one of the pillars has been lost or affected here? And so you have to really think about it. You have to pick one, you have to pick a word, and then maybe you can provide a reason why you think it's this one. So if I asked you here, so why is it that code affects availability? What's the reason behind it? Who can tell me?
If you can't read the message board, then none of the information or data is available to the users. So it's not accessible. And if it's not acceptable, then obviously availability has been taken out.
And why can't you read it? What's going on with this? What is this JavaScript doing?
I'm not really super savvy with this stuff, but I'm going to assume, just judging from reading the slides, that it's redirecting to a different site anytime you try to view the message board.
Okay, one of them is document location redirection, right? You're right.
Yeah.
Exactly, the top one. What about the bottom one?
It almost kind of, it's some kind of loop. It almost just kind of, I'm not quite sure what the loop is for, but I'm going to assume it's just kind of tampering with the way that the the message board looks potentially.
Yeah,
But
it's an infinite loop, right?
yeah,
Whenever we learn how to program, right? Remember that time you wrote that infinite loop? Well, that's basically what's happening here. You can inject JavaScript, right? Remember, JavaScript is just a regular programming language in the browser, and it creates a for loop so you can't access your page. Try this in your own computer, and you'll see. And so that affects availability. So there's, an attacker might see your website, they want to affect your message board, so they put that JavaScript there. Every time somebody visits that message board to add their post, all the posts are going to load, including the one that has this. It runs this JavaScript and it just renders the website unavailable. You see that? And that's an example of something called code injections, which is a very common thing that happens. You can cause in a web browser. That's why you need to have certain security mechanisms to prevent this kind of thing. And usually the defense for it is very straightforward. Just what would you recommend to prevent something like this? Both of those code injections. Remember, they're being placed in a text box. Somebody presses a button. It becomes part of the web page. So what do you think? Just, intuitively, what could you do?
Maybe data validation.
Data validation, input data validation. Very good answer. Exactly. It is as simple as that. You write more JavaScript, right? That checks the text box before anything is submitted. And that's it. Good job. All right, here's another one. My friend is a doofus, right? So we trick users into posting. Somebody wrote something. Somebody came in. All right, so we tricked users into posting "my friend is a doofus" on a message board by inducing them to click on a bad URL or open a bad HTML email attachment. Right? In this case, which property is violated that the victim really cares about? So the answer here is that in this case, we've lost non-repudiation. The victim did not insult his friend, yet the system shows that he did. So that action on the system can be repudiated. The user can honestly say it wasn't me. So it's kind of the idea of why we have accounts, right? We have accounts, and usually we would think that our accounts would not permit this, but what happened here is that somebody, again, may have put some JavaScript in the page that you're logged into. When you click on that by accident, it posts a message, it grabs your own session key, so it's gonna say, oh, it was, Mary or Bobby or Bob or Alex, right? So either one of, and so what you want then is you want to have mechanisms that also protect that non-repudiation. You want to make sure that people can't really do that kind of thing. Okay? Are there any questions about this one?
not that I can think of, at least.
All right, no questions. All right, good. Good. Just, again, just motivating with some examples. All right, so in summary, the goal of system security is to protect assets, the network infrastructure, network availability, and confidentiality of data. Some of the major challenges to security are internet environment complexity, right? So you guys know that the internet is pretty complex. There's a lot of systems. You have to protect all the servers, the network, the software, etc. And there's always new threats and new exploits being developed, and that's a key issue. Some of the ways to increase security include accurate authentication, proper authorization, which is access control, confidentiality of the data, and non-repudiation. And we use a lot of tools to achieve these principles. And as I said, one of the main ones that we will look at in this class is the encryption solutions. So sometimes you want to do, before you start with anything, you want to do risk assessment, right? Risk exposure analysis on assets, human resources, the machinery, the equipment, the information systems, the data storage, everything, all elements, including people. And before you start implementing controls, technical controls, you probably want to write a set of policies. You know, there are various types of security policies that are tailored toward different organizations and types of business. And of course, there's laws, right? So without laws, we wouldn't be able to really do a lot of the things, because basically if somebody wants to attack you or do something, they will succeed, right? So you heard recently the case of some kid, I think, who attacked Twitter and took over the accounts of famous people. And so, you know, that, you know, it can happen, but the thing that really helped there, even though they had a lot of controls in place, is the law, right? So this person was arrested because they, you know, they broke some law. And so certainly the deterrence of law is also very important here. All right, so we talked about those terms. All right, so that's pretty much the summary. Now I'm going to get into the details of the lab for next week. All right, so I'm not, as I said, I'm not going to assign a lab that's due next Thursday. Instead, really, I'm going to assign the lab next week, and it'll be due a week from Thursday. Okay, so what is this lab about? Okay, so first of all, it's going to be with the CVM. So you'll be using the CVM, which is nothing more, I should say, than a Linux machine, it will be a Linux machine, and it's a Linux machine developed at Syracuse that is associated with the book that we're using in the class and a lot of the, you know, the labs. And so a lot of the labs that we're doing just basically already have all the software, et cetera, in the machine. Okay, so we're going to be using that, and really we just need one. We're going to be using the terminal most of the time, and we're going to be encrypting things. That's really the goal for the first few days, or the first few weeks, sorry, is to just encrypt things using the different techniques available, understanding what pillar that technique is addressing, and also then understanding some of the aspects of the technique, right? So, you know, what is the algorithm? Now, we're not really going to get the goal here, and I should stress this, is not for you guys to become cryptography engineers and for you to write cryptography algorithms. In fact, you should never do that. You should never go to your company and say, hey, I'm going to write all the cryptographic algorithms for my business. You should not do that. You should actually just use the algorithms that have been tried and tested for many years, right? And so that's one of the things that we will learn. But at the same time, even though you're not going to be writing, you know, the algorithms, it will help to have a basic understanding of the logic behind it, right? So that you understand, oh, well, this is how this works, right? And so that's really the idea. So when appropriate, we will look at algorithms from a high level. We won't get into all the complications. Usually I'll provide code and I'll explain. And some parts I'll just say, you know, we're going to use this function, this part. And really the focus will be on understanding the parameters that you have to change whenever you're dealing with cryptography. All right.
When did you say it was due?
Go ahead. Sorry?
When did you say lab 1 is going to be due?
It's due, it's due 2 weeks from today. How about that?
Sweet.
Yeah. So no lab due next Thursday. I just want to make sure everyone, but then after that, we're going to start, you know, hitting it hard, right? So it's just this week, kind of get everyone situated. But I am discussing it, though. I'm going to discuss it today. I'm going to discuss it next Tuesday, and then next Thursday, pretty much, I would think you guys, I mean, it's the first lab should be easy to the point where you can finish it on that Thursday, in my opinion. Okay. Any other questions?
So next Thursday will just be like a lab work day or whatnot?
It would be like a lab work day. I'll be there and I'll kind of walk you through it a a little bit. We'll go over the VM and some of the commands and things like that. So I'll probably do like a Linux review either on Tuesday or that Thursday as well.
All right, cool.
A very, very quick Linux review, but I'll do something with that. All right, I have another question. Okay, yeah. So we will cover it up. I think probably I'll do the review on next, yeah, we'll see. We'll see how it goes. All right, so anyway, so what is this lab going to be about? Okay, so now this is where I am introducing the ideas. And so this lab is about certain things, right? It's the main title of it is, I think, the secret key lab. But really what that means is that it applies to something called symmetric key encryption. Okay, so it's going to do symmetric key encryption. Can't remember. Give me a second. I'm going to try to. See if I can write on this. Okay. All right, you should be able to see the slides now, right?
Yeah, I can see them.
Okay.
I had a quick question.
Oh yeah, go ahead.
Because I was looking at the lab one in Brightspace is because I know you mentioned that the seed lab VM should have everything we need, but I noticed a part of the lab is to install OpenSSL and ghex. Is that stuff
Right.
already installed? Or?
You don't have to install it. It's already there.
Cool, thank you.
It's already there. That's the main reason why we use that CVM, is to save you the trouble of having to install all those programs. All right, so so I got my pen to work, or at least it was working. Oh, there it is. Okay, so there's the pen. So basically, cryptography is divided into, we can divide it into two major areas. Symmetric key. You guys can see my writing, correct?
Yeah.
Yep. And then also asymmetric encryption. All right, so that's really one of the main things that we're going to learn this semester. Okay, and symmetric and asymmetric have certain advantages and disadvantage, and also it has each one has a different purpose. So in your previous classes, I'm sure you guys have seen this. So can anyone tell me what do you think is the difference between these two, or what are some differences? Feel free to speak.
One is just going to be using one set of keys, and the other is going to be using a public and a private key. Right,
exactly. So you said it. So one key here, one key here, and then here you have a pair of keys, right? What is called a public and a private key. You need both of them, right? And so basically with secret key encryption, you really provide security, right? Once you have the key, you can have a secure communication. All systems, everything on the internet basically uses both symmetric and asymmetric encryption. They're together, so they're used together. One is the key that you're going to use for the encryption process, and then asymmetric is really the methodology that you use to exchange the key. So if you think about it, this provides the exchange mechanism between two parties, let's say Bob and Alice. Bob and Alice want to establish a secure communication. They need to have a secret key. But how do they exchange that secret key? Well, they're going to use asymmetric encryption. And so we will spend roughly 6 weeks or so just on this idea alone, okay? Just on this idea alone, because there's quite a bit involved in this. And so in this lab today, we're gonna, or this week, we're gonna start getting into the idea of symmetric key encryption. What are the algorithms historically? There's something called DES. The more advanced one is AES, the Advanced Encryption Standard. We're gonna talk about them historically. At some point, we will look at the code for this just to get a feel for how it works, all right? Now, we're gonna learn that symmetric key encryptions or symmetric key encryption techniques can be divided really into two things, which are called stream ciphers and block ciphers. So that's something else that we're gonna learn about. And then whenever we're dealing with blocks, what that means is that, you know, we have, let's say, some text, right? And that text needs to be broken up into blocks, right? So we're gonna break the text into blocks. And then by breaking into blocks, then now when we start encrypting, we're gonna encrypt this block, then we're gonna encrypt that block, then we're gonna the next one, and so on, right? So we're gonna do the encryption in blocks. And usually symmetric key encryption, as I said, can be divided into block ciphers and stream ciphers. The block ciphers, which is the main one we're gonna discuss, are encrypted in blocks. And so we're gonna look at the algorithms for that. And we're gonna see that actually there's various ways that I can encrypt something in blocks. I could, for instance, you know, let me do this. So I have a longer string now, I break it into blocks. You can see that here and so on, right? And I could encrypt each block independently. So that is to say, you know, I encrypt one block and that block does not affect another block. When I encrypt this block, it has nothing to do with other blocks. So that's an independent type of an encryption. But other encryptions might say, you know what, I don't think that's secure. And so instead of doing that, I want to encrypt this one first, and then the output of this, I want to use in the encryption of this one. And then the output of this one, I want to use in the encryption of that one, and so on. Do you guys see that? So which one, just intuitively, if I ask you, which one do you think might be more secure? The block cipher, where you treat every block independently, call it A, or the block cipher, where now the blocks are linked. That is to say, to encrypt one block, I have to use something about the other block. So intuitively, just which one do you think might be a little bit more secure? What would you guys say? Okay, so some of you wrote, let's see.
I'm thinking B.
Go ahead. Go ahead.
I was saying I'm thinking B just because it requires you to be able to break more than one block at a time in order for you to actually see one versus A. If you do it independently, it's easier for you to at least do one block.
Right, exactly, right. So that's a good answer. So you know, it might be, you know, when they're independent. So think about this. If they are independent completely, and I have one single algorithm to encrypt these blocks, what do you think might happen if I have letter A? Oh, sorry, let me use a different letter. Let's say I have the letter M here, and I also have the letter M there. What do you think will happen to the cipher of that plain text? It's the same algorithm, same key, same input.
It'll be the same then.
It'll be the same one, right? So you always hear this, right? When they try to break, you know, try to do like cryptanalysis and things like that, they look for patterns, right? They look for specific areas in the code where things are repeating. So think about language. You know, in English, what are the most commonly used letters?
Isn't E?
E.
Vowels.
Isn't it basically just any vowel?
I think it's like E, S, some of the vowels, yes. But if there's certain letters that E, so if you watch, what is it, Wheel of Fortune? Is it Wheel? No, the other one, I forget the name. But if you watch that show, right, the people that guess the letters, they always start, give me an E, give me an S, right? There's certain letters that are very common in language. So imagine if there's an E in there, probably what I should have used. Oops. Should have used the letter E. Right, so now we know, think about this block cipher, right? It's encrypting the same letters, same algorithm, same key, same input. It's always encrypting the same. And it also happens to be the letter E, which is the most common letter in the alphabet, let's say. So now they start to try to crack the code, you see, because what they're doing is, and this is actually quite important because it takes us to a definition of cryptography. Okay, so one of our definitions of cryptography is that, and this again was defined by Claude Shannon, we'll talk about him a little bit later, is that you want the output of your cryptographic algorithm needs to be almost random. That's the definition of a good encryption algorithm. It's literally like almost 100% random. Now that's difficult to achieve, but you want to try to achieve it as much as possible. And here, what are we doing as we're trying to break this approach? We're trying to actually find a pattern, correct? You guys see the point that we're trying to find a pattern?
Yeah.
Yeah, of the E's that are being repeated a lot because, hey, I'm seeing this same encryption a lot. And so you can from there start to see, yeah, that's probably one of the common letters or something. And from there you try to break it. So when you find a pattern in your encryption, that basically kind of implies that that is a good, sorry, the opposite of that, that is a bad encryption technique, okay? And so that's the main idea here. And so now that as I said, we'll go back to this in a lot more detail later, but all I'm saying is these block encryptions, if we go back to them, some of them might be better than others, okay? And that's what this is, the block cipher techniques. So part of the lab will be to explore 4 of them, which are these: ECB, CBC, CFB, and OFB. So all you have to do is, when you do your lab, you're going to take some input, you're going to encrypt it with a symmetric key encryption algorithm, you're going to use the same key, but you're going to change the block cipher technique. So I'm going to say, for this one, I'm going to use ECB, for this one, I'm going to use CBC. And then you're going to look at the results, and you're going to try to interpret, just like I did here, you know, with this idea, you're going to try to say, well, in my opinion, this one is good or bad. You have a question like that in your lab where you have to answer that. Which one might be better and why? And I've already kind of given you the reason why. The hint is that there's a pattern there, and it's because the blocks are independent, rather. Do you guys see that?
Yeah.
Okay, so why is it that the other approach, B, actually might help with that problem of the patterns? What do you guys think? Why might that be the case? So let me put it in another way. If they're not independent, let me actually... looking for some space. Here, let's just write it here. All right. So in this one, the one where they're independent, right? This is E. This is E, and it produces C, right? And they're the same. However, in another method, you got E and E, but the output of this one, the encryption of that one affects that one, the encryption of that one affects that one, and so on, right? So the first question is, when we encrypt these two, my question is going to be A or B. Let's call it, I'm just for completion, I'm just going to say C1 and C2, right? And under this approach, do you think the ciphers are going to be A equal, C1 is equal to C2, or B, C1 not equal to C2? Under the assumption that they're no longer independent, like this was independent, these are no longer independent. So what do you guys think?
B.
Which one, sorry?
B as in boy.
B, right? And why is that, do you think?
Well, if they're all dependent on the previous block, that means that it's always going to be different, which is
It's different, right? So it's saying like there's the same algorithm, the same key, the same input, but there's an additional parameter, which is the encryption of the previous block. And so that block is always going to be a little bit different because it has what was before, correct? And so that's what another approach. You see that? And so that would be, you know, provide for them to be different. Does that make sense, guys?
yeah.
Yeah.
All right, and so that's the lab. I mean, the lab is really, let's see. All right, and that is called, actually, that additional term is called the initialization vector, because what happens is every block, if you look at this block, right, it depends on the previous one. But what happens to this one here? This one doesn't have a previous block. So it'll just have what is called an initialization vector. And that initialization vector is nothing more than a random block of the same size as the blocks. Okay, you have to pick a block. That's why, so for instance, you probably have seen this when you talk about encryption or read about encryption. You've seen like, oh, we're using 128, you know, bit encryption or 256 or so on. And that, you know, that is used sometimes to determine the size of the blocks that you're going to be using. All right, so your lab then, as I said in summary, is going to include symmetric key encryption. You know, just introduce that. Then it's going to have you work through some block cipher techniques. It's going to include padding, so that you're going to have to deal with that. So what do you think padding might be here? What do you think that might be?
Just a way to fill out the block.
Exactly, right? Because here, imagine your document and then it ended there, right? Or, you know, your information, this last block only came out to there. So what happens to this little piece here to fill up the block, right? So then you have to use padding for that last block so that all blocks are the same. You know, for instance, in a sentence, that would just be, you know, spaces, right? And so when you actually print that out, it's just going to print out spaces or something like that. All right, so we're also going to explore that. So as you can see, understanding symmetric key encryption and so on requires you to understand, you know, from a standpoint of the program, how it works, you know, breaking it into blocks and so on. At some point, I will ask you I will show you the code or the pseudocode for the DES encryption standard, which is, you know, it's the simplest one that we really want to try out as far as programming. You will see it's not that complicated. It's just a bunch of for loops and then some operations. We'll talk about the basic operation that is used in encryption, okay, which is, you know, one specific one. And then the other thing that we're going to cover, I believe, in this lab is data corruption. So what happens, and that's where ghex comes in. So, you know, if you looked at the lab already, there's a program called ghex. I think I actually put a link to this program on the Brightspace just in case you couldn't find it, but I think it's there. I think it's ghex2 actually on the command line. So let's say that we grab a file, we encrypted it, and now we want to flip just one bit. We want to just corrupt it. And so, you know, you're going to explore that. And you're going to explore it. Here, we're not going to be exploring integrity per se, but instead we're just going to be exploring the fact that what happens if we just flip one bit of the encryption, right? Do you guys see that? So again,
Yeah.
let's look at that example. So let's look at the example of, oops. You know, I have that called A versus B. But in B, they're related, as we discussed. So what happens if I just, you know, this is the electronic code book, ECB, say this is CBC or one of the other ones. So if I just flip a bit, so if I, you know, do data corruption, right? So flip one bit I just flip one bit here versus flipping one bit, and I actually flip it like there. The direction is like that, right? And this is the initialization vector. So what do you think will happen if I just flip one bit for this one? So let's say you have the message, which is called the plain text. Then the plain text becomes the cipher. Then you flip. Then the cipher becomes, once again, the plain text, right? So basically what we're doing here is that we're going to take the original message, encrypt it, flip a bit in that cipher. After flipping it, the cipher gets decrypted and back to plain. So under a circumstance, what do you think will happen to the message? What's the message? Yeah, go ahead, please.
Plain text is probably going to be different because it's not, the cipher's not going to be able to go back to what it initially came from since the bit is different.
Under which scenario? Under which scenario?
To be honest, I would think both of the scenarios.
Okay. All right. Good. Good. Let's see. Did somebody say something? I don't know. So that's what the lab is for. Or somebody wrote something. That's what it is. Only that one section of the text might be corrupted for A. Yeah. So that's what the lab is for. You will actually do this problem. You will actually do this problem in your lab and you will explore, okay, is it A or is it B? Okay, so you're going to explore both A and B and, you know, and view. That's what you have to actually report in your lab. When you complete it, you're going to, you know, write your report to me and you're going to say, okay, you know, this one, it's ECB or ECB is like this, and here's the evidence. No, CBC is like this, and here's the evidence. Make sense? So those are the problems in your lab. As I said, I think this lab is quite easy, to be honest. It's very fun. It's a fun lab. All right. Are there any questions about anything or about any of this?
Not about like block ciphers or encryption. I was just more so wondering how the lab report needs to be structured for when we do the lab.
Yeah, sure. So the lab report, please submit a PDF. It should be basically you maybe want to copy paste the seed lab questions, paste them in, and then just provide, you need to provide usually what you did. So that's going to be the command. Sometimes there will be code. So in those cases, you can submit code. But if there's no code, then the commands on the terminal, right, that you follow to perform that task. So it's usually going to be, okay, here's my plain text. I applied these commands to encrypt. These are the parameters. I got the cipher. Here it is. And then I did whatever. Then I do the opposite. I decrypt. Here's my key. And I get the plain text back. So you really have to provide the commands and screenshots of what it looks like in Linux, okay? And the way that you should think about it is, okay, with what I just showed in the report, do I convince the person reviewing this homework assignment that I've completed the task? So that's really what yeah. So I want screenshots of the output. So usually, you know, when you program or when you, and you will know, it'll become obvious, right? Whenever you do something, you will know, oh, I did it. That's it. And so provide that screenshot, but also provide the commands or the code script, script, and also some description. Provide, doesn't have to be, a huge thing. Just 3 or 4 sentences, kind of in your own words, explain it, just in your own words, okay? I'm not checking grammar, but at the same time, make sure I can read it. That's all I'm saying.
All right, cool.
Make sense? Yeah. Yeah, so like I said, so this first lab, that's why I take it slow in the beginning. I'll try to grade it as soon as possible to give you guys feedback of what you did right, what you didn't do right as far as presentation. But it should be pretty straightforward. But good question. Are there any other questions about that?
Not that I can think of, at least.
All right, no questions. All right, so let's keep going. So we're talking about the lab, right? We're talking about the lab. And so we talked about, these are the components of the lab. And now block ciphers. So so we talked about this. Let me erase this because just want to. Address this slide. All right, so block ciphers, just a little bit of intuition, as I've already said, kind of in words. Block ciphers use a chaining mode, okay? A chaining mode. And that's what is these are called, right? The block cipher techniques, right? They use a chaining mode. We will see this in more detail later, but block ciphers use a chaining mode that indicates how to encrypt blocks of plain text M1, M2, all the way to MM, to produce corresponding blocks of ciphertext C1, C2, C8. And that's really what you're doing. So whenever you are encrypted a message through block ciphers, you have an original message, gets broken up into blocks, right? Then it goes through some type of an encryption algorithm, right? And maybe a key is applied, key, right? And you perform an operation, right? You perform an operation with the key. And we'll talk about that operation later, right? And that process basically gives you what is called a cipher. And the cipher is just, whereas this was M1, M2, all the way to MN, these are now C1, C2, ... CN. All right, so this is what you're going to send to your friend. So if you're Bob, right, Bob, then you're sending this to Alice. And then Alice is going to receive this information, and she's just going to do the reverse of this process through the decryption algorithm. So that implies that there's going to be an encryption algorithm and a decryption algorithm. But in its simplest form, they're both pretty much the same. They're just an operation. And what matters is that we just have to know which blocks we are dealing with, okay? All right, and so that's what, and so we have to understand that process and how to reverse the process to obtain the original plain text from the cipher text. Okay, so that's one of the things that we will also explore in this lab. So the modes of operation, or the chaining modes, as they're called, is what I was saying, right? So what I've been explaining, all of these blocks are different ways in which you try things. We're mainly just going to focus on 2 of them, but there can be many schemes. So the main one that we want to look at is ECB and CBC. Although in your lab assignment, I believe it'll ask you now try CFB, OFB if you're going to be comparing all 4. But as far as looking at them from the point of view of the algorithm, the code, we may only look at 1 or 2. So electronic code book, basically, just to give you a definition so that you have it. The plain text is split into blocks, and the blocks are encrypted independently. That has been the key word, right? Talked about that. The CBC is called the cipher block chaining, okay? Where plain text is split into blocks, and then each block is XORed, and XORed here, I just introduced that. Anyone know what XOR is?
I remember like doing the XOR operation, but I'm not quite sure how to explain
Yeah.
it.
So let me just put it this way. At some point you learn about truth tables, right? You learn about the truth tables, and usually there's like, if I have a true and a false, and and if I do an AND or an OR or an XOR, right? And so that's really all that we have to worry about. So at some point in the slides, in the lecture next week probably, I will give you that truth table for XOR, and then just be aware that that's the operation that you want to do, because at the end of the day, think about it, you'll have a key, right? And then you have a message, the plain text message. And these will be probably text, right? You'll have text in there, ASCII characters, but that gets converted into binary. And binary. Do you see that? And so now what you end up with is you end up with a key and a message that are binary. Let's just say like 01101, and then this is 11010. So all you have to do is you apply an XOR operation, you get the result of that, that's your encryption. That's it. Do you see that?
Yes.
Yeah, that's the major operation, that you apply an encryption. And the reason for that is that encryption, imagine a movie. Imagine you want to watch, what's a good movie that just came out in Netflix or something. I don't know, but something, the movie that came out a couple of years ago, Avengers, right? The Avengers one. So you want to watch the Avengers. How long does it take from the moment you click Avengers to the moment it starts, you think? Pretty fast, right? It starts really quickly.
Yeah, a few seconds.
A few seconds, right? Probably. And if you think about it, that's a huge file that was sent over the internet. They can't send it unencrypted because people would just steal it, right? People who don't have a subscription would just take it. So they encrypt it. And so imagine if you create an algorithm that's very math heavy with a lot of operations and calculations and so on. How long do you think it would take before you can start watching your movie? A long time, right? Do you see my point?
Yeah.
Yeah, and so encryption needs to find a balance between security and performance. Computers are very good at performing these types of operations. And so therefore, you want to build something that's fast. And so you build the complexity on this, and you actually don't rely then. My point is that you're not really relying on these very complex algorithms of, oh, this step and that other step. It's really about this simple operation, but what's important is that the key should be a random sequence of bits, because the more random it is, the more random the message will become. You see that? So really a lot of the emphasis is on here, on this, on the randomness of the key, and then the sequencing. But really the operation is not that complex. Are there any questions about that, guys?
So mainly it's
go ahead.
just putting more emphasis into randomization, but keep the actual operation itself simple. That's how it's normally.
That's right. That's a
performed.
good way of putting it. The operation is very simple. You will see across a lot of the things that we do that it's XOR. It's an XOR operation. And then that's why one of the reasons why we covered the data encryption standard, even though that's not the secure algorithm anymore, you'll see what it is. It is ultimately keys that are random, the more more random keys, and then a couple of steps, but all operations are XOR operations because you need that to be quick. Yes. And then when we look at RSA, RSA is a little bit different, but that's why RSA is not really used for confidentiality, is only used for authentication. Because the authentication only needs to happen once. So you can afford to take a little while to just exchange a little bit of information, but you cannot afford to take a little while on millions of blocks, if that makes sense, because it's really going to slow down things. I mean, you know, security is important, but if your movie starts, you know, on next week, you're just going to go to the movie theater, right?
Right. And so
Yeah.
RSA would be something like Netflix or streaming services would use, just the initial authentication, and then you're good to go.
That's right. Exactly like that. Exactly like that. So an RSA algorithm will be a little bit more complex. We will study how that works. There's a little bit more code involved in operations, but it's really just for a specific task. And then at the end of the day, the workhorse that does the heavy lifting has to be something like XOR. As long as you make this key, you exchange it securely, and it's a good key, long and random, you know, everything will be good. Make sense?
Yes.
All right, great. Anyway, so again, just giving you some background today on the lab, right? So these are the tasks. So you'll be doing, so I like to, you know, I don't want you to just type like, oh, now I'm typing ECB without really understanding why you're typing it, right? So the reason why you're doing that, as I said, is this difference that ECB is independent, whereas cipher block chaining, the so-called CBC, plain text is split into blocks. And each block is XORed, so we understand that now, with the previous block to get the cipher text block. And so we're doing that. They're no longer independent. And then we have other methods that you will explore. We're not going to spend too much time on this, but you know, basically cipher feedback, that's going to be similar to CBC, but a different algorithm. And that's usually what happens, is a different sequence of steps. And then the OFB, or output feedback, is what is called a stream cipher approach. So to really understand this type of thing, remember what I said at the beginning, with symmetric key encryption techniques, symmetric key, we have actually block ciphers, and we have stream. Just doing that. Stream ciphers. Oops. All right, so it's doing, so we have both of these, right? So in symmetric key encryption. And so we're going to spend a lot of the time with the block ciphers, but we will also at some point explore the stream cipher. And the stream cipher is just kind of, just to give you some information right now, whereas in block cipher, we kind of take the entire document, break it into blocks, and use it like that. With the stream cipher, it's almost on a byte per byte basis. So it's almost like, think about it like a faucet, right? So you have a document, and then you just grab one byte, send it, XOR it with some key, right? And it goes its way, then the next one gets sent, and the next one, and so it's kind of, it's called a stream cipher because of that, because you're doing it on a byte per byte basis, okay? But we'll see a little bit more of the details of that one later. This lab does not include that much on stream ciphers. All right, so we talked about the modes of chaining, or modes of operation, chaining modes, okay? And then finally, the initialization vector that I talked about, you will see that in your lab as well. And that might confuse you at first because it really just seems like a key. But I'm going to put it into context here. What's happening is, let's say you have an original message like that, and then you break that message into blocks, right, as I said. So if you're trying to use, let's say you want to encrypt, and these are like M1, M2, M3, M4, M5, right? So you want to encrypt M5. So what needs to happen with M5 is that you're going to get the key. And the key goes in there, but also the output from the previous one. So let's say this gives me C5, right? And so for C5, I need, let me do this. I have an XOR. I have the key that goes in there. Actually, it's going to make things complicated. So I'm just going to put the key like there. And this is a key and goes there, right? But also, the output of this, C4, now goes here. You see that? That's basically what's going on. Then the same thing goes over here. I have M3, perform an XOR. I have a key, goes in there. This produces C3. C3 goes in there. You see that? And then I do the same with this one over here. This is C2. I have an XOR. Okay, I have the key. Goes in there. This produces C2. This C2 goes there. Right? So you XOR both of these. And finally, here I have C1. Right? I XOR, have the key. All right. This C1 also is used for the next operation, but then the algorithm will have a problem. What's the problem here? What would be the problem?
There's nothing for, there's nothing to be used for M1s.
There's nothing to be used for M1. Perfect. And so we need, if we're going to follow a consistent algorithm, we need something there. And guess what? That is called the initialization vector, the IV. All right, and so what is the property of the IV? It needs to have the same dimension, so n, and the size of the block. So this one just has to be the size of the block. What does it have to be? Well, it doesn't matter because all of these are just going to be binary, right? So it's going to be 1, 2, 3, 1, 2. They're just going to be binary. And so this one can just be any random thing, or you can, or just like when you do this in the lab assignment, you're going to have to create a key. And the key, you don't have to type in a binary key. You can just type in a letter. So it's going to be like A, B, C, that kind of thing. And then your IV is also going to be, another 1, 2, 3, whatever you want it to be. You just have to be consistent that the algorithm uses that. Okay, so that you can, because remember that you have to do the process forward and you also have to do the process in reverse, right? So that's really the only issue there. Okay, so that is called the initialization vector. This is, pretty straightforward and a lot of fun, so it should be easy to do. So the official definition of it is that the initialization vector is a block of bits that is used by several modes to randomize the encryption and hence to produce distinct ciphertext. Okay, and so this idea here, you can use it in I could devise a scheme where I, do whatever I want, right? So you can try various things, but at the end of the day, in general, it serves that role. That's why it's called the initialization vector. Are there any questions about this part, guys?
I don't think so.
All right, great. So seems like we're making sense. All right, so let's I think this is the last slide. Yeah, that's the last slide. Okay, so that's really the lab. I hope that makes sense. So now what I'm going to do with the rest of the time that we have available is I'm going to go to the lab document itself, kind of show you how that works. And so let's do that. So I'm going to stop sharing here. And I'm going to go to, I want to show you one thing. One thing is you can always go to, hello? Yeah. You can always go to the seed labs. So Okay, so you should now, I'm sharing the website, the course website, the Seed Labs that ties into our book, right? So as you know, we're using that book that I suggested. What is it? Right, this one, right? Computer, Internet, and Security. All right, and so you can take a look at that. But I just want to stress it, if you're new to this, that we're going to be using this lab, this VM, right? The VM here. If you have questions about setting that up, you can go to the course website. Are you seeing my website, guys?
Yep.
Yeah.
So if you go to the course website, I've posted some instructions here. So under useful, you can download VMware Workstation. I was told by Donna that this somehow gives you the license. I believe you have to log in, I assume. Then I just showed you this, right? So that's just a link to the VM. You'll need to download that. And then I posted some instructions on how to create the seed VM, right? So I was told by, this usually works in the past. Also remember, we have a resource, Mitch, Mr. Burke, who is a grad student, and I believe he told me that this works pretty well. So if you have any questions, as I said about this, let me know if these instructions are somehow not correct, and just send me an email and also copy Mitch. Okay, but I thought a couple of students tried this and it worked for them. So, but we'll certainly work with you to make sure you have your VM. Okay, so I wanted to say that. So that's going to be the lab environment. Then the other thing I wanted to show you is there's more materials. So the book comes with this. And then if you want to find a corresponding lab, you can always just click on Seed Labs over here, right? Click on Seed Labs. They're divided by VM. So we are using 1604 currently. And then you can see all the labs are here. We are doing the cryptography lab, so you can click on that. And there's a lot of labs all the time being generated. We are working on the secret key lab. Okay, so we'll be working on this one, secret key encryption. So you can click on that. There's the associated VM. There is some of the files that you can always download. It tells you where in the book the chapters, the corresponding chapters are. So I encourage you to please go ahead and read the chapters, right? Read the chapters before next week. I will, of course, provide a condensed explanation of some of this. I've already done explanations of all of this. We won't do everything. So we won't do every question in the lab necessarily. We'll just do a few ones. I mean, you can always do the whole thing. That's perfectly fine. But I will just be addressing some of them, some of the questions. You can click here. This is the PDF description. You can click on that. This is the updated version. So I suggest you use this one. I think in my Blackboard, I just have like an older version of that document, but we will be doing this. So go ahead and download this one if you'd like. It's pretty much the same thing. Let me just. So this is definitely the one to use it, and you can see. I'll read through it, of course, but this is the lab, right? I have a question. Let's see. If you read, do you mean on the website? What do you mean? Oh, where it says chapter 15, chapter 8, and chapter 21. Is that what you mean? Yes, what happens is, I believe, so this is what I had said initially, right? That I recommended that you use this book because the way I think I've looked at these books is that the other books, computer security and internet security, are just abridged versions of the bigger book. So there's a bigger book, computer and internet security. I think if you just buy that one, then you have everything. so that you don't have to buy the book separately. I don't know, I don't remember the actual cost, but I assume it's probably cheaper to buy the book that has both topics than to buy the other books independently. I can't imagine that he's writing 3 books. He's just writing one and then breaking it up into the pieces. So so if he updates anything, it'll be this one. So what I would say then is, to answer your question, is probably just read chapter 21. Do you know what I mean? Yeah, okay. I have the book in front of me here, so let me just take a look at it. And as I said, I will explain this next week. Now, I don't necessarily just cover his material. I have a few notes from the Bonet book as well, and so that will make its way in here. But so I'm in the book right now. Yeah, so chapter 21 of Computer and Internet Security is secret key encryption. Okay, so it ties really well with this lab, which is called secret key encryption. And as you can see there, the topics are substitution cipher, which is just like, like the insecure type of ciphers. Then it talks about data encryption and AES encryption algorithms, which I will talk about. Encryption modes, I kind of gave a hint of that. Initialization vectors and common mistakes. Programming using cryptography APIs. So we may not spend too much time on programming and using cryptography APIs. I'll take a look at it. I'll give you some code. I think, I don't know if he's using C. No, he's got Python. Okay, yeah. So I also use Python in a lot of the stuff I do. And so, but he's got some of these programs in C and C++. And so I'm not going to emphasize anything in C++, but just the ones in Python. And then he's got authenticated encryption and the GCM mode. Yeah, so read chapter 21 basically, okay? Read chapter 21. It'll tie in really well to the lab. It's got a little bit of history there on the Enigma, so that should be pretty interesting. It's got, the diagrams for ECB and CBC. I will cover that as well in the class, in the notes. I will just be writing a lot of this on the board. I enjoy doing that. It's got some of the commands. So one thing I will say, this book is really helpful to solve the labs. It usually has, a lot of the commands that you need. And so certainly reading it will save you time later. Okay. Yeah, and then he's got some programming. Pretty good. Yeah, chapter 21 is very short also. It's only, like 20 pages or so. All right, and then the next chapter is chapter 22, the one-way hash function, and that's the next lab. Hashes, what principle of information assurance do you think hash functions addresses?
Integrity?
Integrity, there you go. How about secret key encryption? What principle of information assurance do you think it addresses?
Confidentiality.
Confidentiality, exactly. So you're getting it. And so that's basically what we will be doing. So next week 3 probably we'll get to integrity. So it's chapter 22. And then chapter 23, that's the next lab, public key cryptography, and so on. So you get the idea. Read the chapters, they will help you quite a bit with the labs. And then I do have some additional material, but it all works pretty well. Okay, does that answer your questions as far as chapters in the book, guys?
Yeah, definitely.
Okay, great. All right, so now let's just keep going. Let's kind of finish up today with the lab. So I'm going to just click on the description here. I thought I had clicked on. Can you guys see the PDF?
Yeah.
Okay, so please definitely go through this one, okay? Use the one that's on here. I think if I look at the one I posted on Brightspace, the old one, I'll probably change it. But if I forget for whatever reason, just be aware it's this one. They're basically the same though. So really we are going to cover we are going to focus on task 2, encryption using different cipher modes. Task 3, encryption mode with ECB and CBC. Padding, which is task 4. We'll take a look at that, at least partially. We're going to skip task 5, which is error propagation, corrupted ciphertext. We might, or actually no, we may do this one as well. And then common mistakes with the initialization vector, we're going to skip that. Task 6. Then additional readings. And definitely we're not going to do programming using the crypto library. I don't know that I want to get too much into this, but I'll see. Let me think about it.
Will you provide a list of the tasks
I will.
that we
I
have
will
to
provide a
complete?
list. When I create the, usually what I do is when I create the Dropbox on Blackboard, you'll see me do it in class. When I create the Dropbox, as you guys are working through the lab, I'll say, go to the secret key encryption lab, and then I'll say complete task, 5, 4, and so on. So I'll provide that there. I just, I want to think about it if I'm going to give you everything or not. Okay, we'll see. But yeah, that's it. So this is the lab. Does this make sense, guys?
Yeah.
Okay, so let's just kind of go over, let's finish up going over the details of the lab. So this is the secret key. So the overview. So the learning objective of this lab is for students to get familiar with the concepts in the secret key encryption and some common attacks on encryption. From this lab, students will gain a first-hand experience on encryption algorithms, right? So that, you're going to start with that. You'll be using OpenSSL, encryption modes, which is what we talked about, ECB, CBC, paddings, right? So, adding for the blocks and the initialization vector. Moreover, students will be able to use tools and write programs to encrypt and decrypt messages. All right, so we'll do probably more scripting later. I don't think we're going to have to do it in this one. Many common mistakes have been made by developers in using the encryption algorithms and modes. These mistakes weaken the strength of the encryption and eventually lead to vulnerabilities. So this lab exposes students to some of these mistakes and asks students to launch attacks to exploit those vulnerabilities. So the idea there is actually pretty important. It's what I had said, that you don't really, first of all, you don't want to, at your company, you don't want to implement your own algorithms, right? So instead, you're going to use like Linux's well-established OpenSSL program, right? You're going to use that, first of all. Because what happens is, as you know, it's a community that develops these algorithms. There's no security through obscurity. I want you to understand that. There's no security through obscurity. And what that means is that people know the algorithms. The algorithms are well known. It's not like any details of the algorithms are hidden. You get that idea? It's not about the algorithm, it's about the key. You protect the key, and you know that given that algorithm with a secure key that has been kept secret, you know that that algorithm is secure, okay? So it's not that you're hiding any details of it other than the key. The algorithm is well known, people can have tried, and that's the key aspect here, is that people have tried to break the algorithm by knowing all the details, but without knowing the key, they were unsuccessful. Okay, so that's really the idea. There's also a difference between the algorithm that has been described, right, in some protocol, some standard, versus the implementation of that algorithm by a software developer, because the software developer may just have implemented the algorithm wrong, right? So that's what you're gonna look at as a student in this course, is that it's possible that you understand the algorithm really well. People have told you that the algorithm is pretty secure, but then when you actually try to implement it, you made a mistake, and that mistake resulted in a vulnerability. Okay, so that's another idea there. So I would say that a lot of the coding that we will do in the class is mainly for understanding purposes, but it's never intended for you to actually write code for encryption. You instead want to rely on well-proven, well-tested, for RSA, for instance, they used to have a competition for like many years, and every year people would just go there to try to break RSA, and so that's really what you want. People know the algorithm. There's no security through obscurity. It is well tested. Okay. All right. Anyway, so this lab covers the following topics. As I said, secret key encryption, substitution ciphers, frequency analysis, encryption modes, IV, padding, common mistakes in using encryption algorithms, and some programming. So really, as I said, once I post the Dropbox for this next Thursday, I will let you know which things I want you to focus on. All right, all the details are there about the reading, the VM, and then these are the problems. Okay, and so you would work through them. You might, when you write the report, you would copy paste it, I suppose, the information, and then post your answers. And then finally, here's the instruction submission. You need to submit a detailed lab report with screenshots to describe what you have done and what you have observed. You also need to provide explanation to the observations that are interesting or surprising to you. Please also list the important code snippets followed by explanation. Yeah, so don't just like paste. I've had students that just paste like pictures. Please provide a little bit of a description, okay? And that's it. So that's it for today. That's the discussion of the lab assignment. As I said, next Tuesday, I will start getting into more of the details of all of this. And then this lab will take on Thursday, okay? So we'll stop here for today, and I'll stay a few minutes. If anyone has any questions about anything, otherwise, you can log off, and I will see you guys on next Tuesday. Have a nice weekend.
Thank you. Have a nice weekend.
Have a good one.
You too.